Hello everybody, today we'll be doing a print leaf node and print leaf node reverse. So given a binary tree, print all its leaf node from left to right, and as the extra challenge, if we are asked to print the leaf node from right to left, how would you change your solution? So here we go, we have here our test cases. This is our understanding part, as well as our review part, all in one. So with our understanding, we create our function to print out 4, 6, 7, 9 because these are the leaf nodes of our tree from left to right and from right to left. We have 10, 9, 7, 6, 4. If some edge cases that we can think about at this point, this is the happy case, is if there's nothing, we should output nothing. With that, I think we're ready to go. So let's just empty this out, and we're gonna print reverse none. Perfect. With that, we should return nothing, and we should be good to go. With that, let's do a match. So our matching is that we're gonna do a recursive approach to this problem, and recursively get every item using a depth first search. By using a depth first search, we would be able to move down the left side, grab this item, and send it back up. Then we would go down this route, grab these two items, send it back up, and grab these two items. Every time we grab items, we send it back up with the left and right, we add them together. And that way, at the top, we have all of these nodes for ready to print out. So our match is going to be recursion, and our plan is to reach the node without left or right pointers and return that value. Otherwise, we'll just return that value. So let's get started and check it out. So here's the plan. If not root, we're gonna return nothing. That handles our first case and also the base case. So otherwise, if root dot left is equal to none, and root dot right is equal to none, then we have our root dot val. So we return string of root dot val. Otherwise, what we're going to return is just the print left node root dot left plus the print print leaf node nodes root dot right. So with that, I think we're good to go in terms of the first function. Let's print that out, and actually, yeah, that should work out. We'll add a splitter between each particular item. So first things first, let's run it and see what we get. Oh, we have an error. So equals done. So a way to do that is simplify not and not. So we've simplified that code. A problem is that, oh, there's no code down here. So what we need to do is reverse it. But if we reverse it immediately by just switching this to right and left, what happens is that this does not swap the nodes properly because we just swap these nodes in front of this node. I'll show you when we return. But what we actually need to do is reverse the entire binary tree and then print it out and then reverse it all back again. However, a better way to do this is to create a string, and using that string, we will just do a reverse on it. That's much better because we don't have to reverse every binary node. But at this point, there is some indentation block. Let me go just fix the bugs, and then I'll be back. Okay, I fixed the indentation bug right here, and we are back. So as you can see, there is some like excess space here. So what we need to do instead is set this to S, and that's our string. So what we're gonna do is string.split, and we're gonna join it with a proper just one spacing, and we're good to go. Otherwise, we can print it out. I mean, if we're just looking to print it out, it doesn't have to look any other way, but this would work just fine. As you can see earlier, like I predicted, this swapped the whole entire bottom row and moved the top row to the left and right. So that didn't quite work. We needed to reverse the whole binary tree to do this. Maybe there's a better way, and I did not think of it. So what this can call is, instead of all of this code, we can actually call print leaf node at root. So let's set that as S, and then we'll return the s dot reverse. I mean, like reverse that. Run. Left node. My bad. Leaf nodes, please. So let's run that. And it looks like it's false. That's because it was split too early, and what we were returning we'll return the digit in the half. So looks like we are unable to do that like we wanted to because of how we reversed the 10. So what we're gonna do instead is, after the split, then actually, never mind, my bad. So what we're gonna do is split this back up, and then reverse it, and then join it back again. Right. Great. We have solved both problems. And I don't know if this is exactly what they wanted us to do, but we have basically done the problem. Let's look at their evaluation. This is going to take O of n time because we have to access every node for each node. And this is going to take O of, let's say, the height of the tree. We don't know what the height of the tree is, but it is the space for recursion. Like I said, what we're going to do is we're going to go from each layer to the next. And once we finish this layer, when we return, that layer is returned back to the memory stack. And as we go down, we have to collect that memory. So here's the memory that we needed to retain at this particular layer. Then we return it back. So with that, we have solved the problem. And should we try the binary search? I mean, reverse the binary tree and then print? I think let's do that, and then we'll reverse it back again. Give me a moment, and I will take a look at that solution. Alrighty then, so I created a reverse binary tree type function. What we do here is, basically, if there's a node, we swap the nodes between the reverse binary tree of the right and the reverse binary tree of the left, and then we return the root if it exists. Otherwise, return none, essentially. So let's check that out, how that works. Basically, we're here, we go in, this goes down, reverse the binary tree. We return a reverse binary tree of the left and right, so we swap those. And we go in here, and we go to down here. We swap the 7 and 6, swap the 10 and 9. Then we swap these in that particular order. Then we swap these, so now we have 10, 9, 7, 6, and then we have 4 on this side, and then we send it back to 1, essentially. This is how we reverse the binary tree. Pretty nice. There's a different way of doing it called creating temp nodes. And, well, I mean, we can write it out. Yeah, why not write it out? So, okay. So a different way of doing this, I think this is the way it works the best. But I mean, if you want, we can define a DFS call, and we'll take in the root. If not root, return none. And basically, it's the same. Essentially, we set root dot left and root dot right equals root dot left and root dot right, and the difference is we run the DFS here, DFS call of root dot left and DFS call of root dot right. It's essentially the same thing. We just swap everything, and all we need to do is just call this of root, and then we can return the root because it has been swapped. So that's essentially it. Let's run it. Well, it looks like it's false right now. That's bad. What happened? Give me a moment. Let me think about it. Okay, so I fixed that bug. We didn't send it to the right place, so nothing is swapped. So we reversed these, and everything looks good. So as you can see, it still passed the test. And essentially, that's exactly what we did earlier. And if you want this to be even more detailed, you could do a temp equals this particular like DFS call and save it and then reassign it. But so what I mean is that we set it to root.left, and then root.left is equal to root.right, and root.right is equal to temp. If we did not have this call, like in most languages, this is what we would do. Let's run it again, and it's all good. So many ways to do this reverse binary tree. So essentially, how it simplifies down is that, well, do we actually need this DFS call? Well, not exactly. Let's remove it. If we remove it, so how do we run this code? Wait, sorry, we took one extra step. Why don't we just put this DFS call here and take this DFS call here? Let's run that. Okay, that doesn't work because we're not returning anything. So how do we return something? So let's remove DFS call and just say if root. Let's swap it and let's return it. And that's how we came up with that code. Where's DFS anyways? Why do we run DFS? That makes no sense. So yeah, that's just basically a simplification of the code. With that, let's go back and look at our print leaf node reverse 2. This is our print node reverse 2, where we print the nodes after reversing them, then reversing it back. This here is to check if we reversed it back properly, which we did. So here, we did a reverse binary tree. We basically spent O of n reversing the tree. Then we spent also O of n to print it, and we then spent O of n to reverse it again. I would say that this would be a slower function than this one here. I think let's time it, and let me get back to you with a time. Alright, we're back with a timer. So how I did this was I imported time, and I dropped in a start time and end time for our method 1 and method 2. So by starting the timer and ending the timer at each particular time when we needed to start and end, so we were able to generate these solutions. So with that, method 1 took 0.003 seconds, milliseconds, and the other one took 0.22 milliseconds. Of course, this method 2 is going to take us much longer to do it, to do 3 reversals, basically, to do 3n, essentially. And this essentially only goes in and prints the leaf nodes, and we just do a reversal on the string. So which one would you choose? I don't know. Depends on what we're trying to learn. Test the skills up here. So with that, is there another way to print the leaf nodes? BFS would not work here because when we're doing BFS, we're printing layers, and as you can see here, this is on a different layer. Unless, yeah, we can do a BFS actually if we just grab all the nodes that don't have nodes below them, and then we only grab those nodes from BFS from left to right. So that will be our first node, and then that will be our second node. That will be a third node, fourth node, and fifth node if we're going left to right. That will work, I think. Of course, we're not gonna do that here. Yeah, I think this method works more naturally for this particular circumstance, and that's why we chose to do this instead. So with that, I hope you enjoyed this video. If you have any questions, please comment below, and if you have some better code that you would like to share, please comment, and I'll see you in the next one. Thank you. Bye.